Okay, good afternoon. Today we're going to start a two lecture series on state estimation. Any of you that have studied much control theory, you know that the control theorists like to talk about state estimation. Estimating the state. They talk about the state variables and state variable control. State variables are just those, that minimum set of variables necessary to completely determine all of the position, velocity, acceleration, and so forth of all the elements of a dynamic system. In a power system, that simply means that we're going to estimate the voltage magnitude and the phase angle. If I know the voltage magnitude and the phase angle, I can say that I know what all the power flows are, all the currents, etc., etc., all the real and reactive power and so forth. We don't try to estimate rates of change, for example. We're not trying to estimate when we're in the middle of a transient situation or any kind of dynamic swings. What I thought I would do, because this is a bit of a different topic than many of you have seen before, we have a power system out here, and one of the things that we do, this is a friend of mine who teaches at Worcester Polytechnic Institute. He came up with this nomenclature, or the symbolic. This is a measurement, okay? Measurement. And you know, I can put a measurement on a load like this. I can attach a measurement off here, and I can measure voltage. And later on, we're going to talk about the fact that it's now possible, given the fact that we have GPS satellites, to get a time standard so that we can measure. We don't measure phase angle. We measure phase angle difference. The truth is, voltage is we measure the voltage difference across two phases. That's when we talk about voltage, we're talking about phase to phase, and then of course you can get back to phase to neutral if you want. But these are, you know, and here we're usually talking about P flow and Q flow. There's P, there's Q, there's P, and we telemeter that, meaning we take these values and we measure them, and we bring them back through communications channels. Now, the communications channels can be telephone circuits, can be microwave communications, could be satellite. I don't think anybody that I know have ever heard of that, but could be. Fiber optic, where you put fiber, you twist fiber onto the ground wires of the transmission lines. You get a tremendous amount of bandwidth by doing that, and that isn't going to add anything significant to the weight of the ground wire, so it doesn't cost anything as far as you know, just put it up there, wind it around the ground wire. A lot of electric companies have done that, and then they lease the bandwidth to television channels or any communication company, internet suppliers, etc. You bring it back in, and what we would like to get out of it, is a model, and I'm going to draw the power system down here. We'd like to get out of it the model of the power system, which is in the computer system, really, and we'd like them to match. We'd like to have a model that matches the flows and voltages out here on the transmission system, and the voltages, the loads, everything. Then if we do security analysis on our model, we know that at least where we're starting from the same point as the actual system. Now it turns out that they realized this a long time ago, and they used to, according to what I've heard, I never participated, but they would send people out to substations with stopwatches that had been synchronized, and they all said, okay, now precisely at noon today, we're all going to take these measurements. We're going to measure the P and Q and voltage, and then we're going to bring all those measurements back. Well, how well synchronized and how fast those people could read them is one source of error, and the problem is that these meters out here, we can put a big, that there's an error in these meters. They all have some error, and when you took the error due to non-synchronous, absolutely non-synchronous reading of the measurements and the meter errors themselves, and you put it in the model, a lot of parts of it didn't come anywhere near looking. They couldn't force the model to match the real system. Now let's talk about that for a minute. There's a very simple example. I did not put this in the book, but I think it's a good one to learn from. So here we go. We've got a bunch of data, and we're going to put data like this, and we're going to say, well, actually there should be a straight line that fits this data. For some reason, when we take the measurements, we don't get everything perfect. We get the X perfect, but the Y is not perfect. So we'd like to fit, and that's the word that's used. We'd like to come up with some sort of straight line. In this case, Y equals AX plus B, where A is not known and B is not known. But it fits this. It gives you a line that's the best estimate of the points altogether. And what we're going to do is we're going to say, well, okay, look, if this is x1, y1, here's x1 right here, then this is error 1, so we'll say epsilon 1. That's the difference between this, and in fact we'll say epsilon 1 is equal to y1 minus this line ax plus b, where this is x1. Okay, so that's what we mean by the error. We'd really like to have a line that went through every point. It turns out that if you want this to fit through every point, you can put you get a high enough order polynomial, and you can make it weave around and pass through every single point, so there's no error. But of course it's meaningless. Fitting a line to a bunch of points, or fitting a quadratic to a bunch of points, is so common. It comes up all the time, and any time you're making measurements, or let's say making measurements. If you're making measurements with out in literally walking around up and down in the field and through the woods, taking sightings, even if you have very accurate laser point sightings, you can get some errors in there. And then in the end, you want to get the survey correctly. You take a lot of extra points, and you're going to have to do this fitting. It actually goes under the terminology of regression. So you need to think about this this regression. Find this. So we'll say error 2 and so forth. So let me an error 2. Here's maybe this is x2, and here's this is epsilon 2, and that's equal to y2. Here's x2 y2 minus, now you might say, wait a minute, that's below the line. Yeah, but we're just going to consider the difference, and we'll always subtract the line estimate of the y value from the actual measurement. So this is the measured value, and this is what we call our estimate. Okay, estimate of y. Given x, that's the estimate. That's what we want. We want this line that will tell us those things. So what we're going to do is we're going to say, well, I'm going to say one way to do this, one very rational way, is to minimize the sum of the squares of the errors up to n. Okay, and we'll go I equals 1 to n, where we have all the way up here to xn, yn. Minimize the sum of the squares. Now, why the sum of the squares? Why not the sum of the absolute value? You can do absolute value. It's a little more difficult problem to solve, but that can be done, and it has certain meaning. We're going to stick with minimize the sum of the squares. Why not minimize the sum? I can drive that to 0 by just having enough pluses and enough minuses. So that really doesn't give us anything. I like minimize the sum of the squares, so that if you have a large negative one and a large positive one, they both give you an error, and so you'd like to drive those to small numbers. And so this says that I'm going to minimize the sum of yi minus axi plus b squared. And I'm given the data for this, and I'm given the data for this, or the x's. Where are the x points and what are the y values? And I want to minimize this over a and b. In other words, those are the variables that I'm going to calculate. Okay? We're going to rework this a little bit mathematically so that it fits the math of the power system equations. So let's go here. I'm going to say, well, I'm going to form a vector y1, y2, and I'm going to say, and I'm going to subtract that with the following: a matrix that's got x1 and the number 1, x2 and the number 1, down here to xn and the number 1, and then it's multiplied times a vector a, b. And that's the statement of that. That actually is epsilon 1, epsilon 2 is now in a vector. Okay? So we're gonna give these some names, and let's see. I think I will do it. I will do it right now. All right, I'll do it in red so you can see that I'm, what's going on. I'm going to call this vector Z. So I'm just going to call that Z. And I'm going to call this matrix H. And then I'm going to call that that vector there, I'm going to call that the vector X. Not to be confused with these values over here. That's in the H matrix. So this epsilon vector is equal to Z minus H X. Now, I want to be careful here about the dimensions. The dimensions. We're going to go with a different color here. We're going to say that this vector here is the length of this is the number of state variables to be estimated. Okay, number of state variables, and of course, so you can just call that NS, and this is the same dimension here, NS. This is the number of points. Later on, we'll call that the number of measurements. But for now, let's just call this the number of points. Now, the state variables, there's only two in there because it's a straight line, so it has two coefficients. This is, of course, also equal to the number of points, as is this. Okay. Well, now, if this is the case, then we're going to minimize the sum of epsilon sub I squared. But that's very simple. We take, and if I multiply epsilon 1, epsilon 2, I'm going to transpose, they call that the transpose of that vector. So this is, and multiplied, I will get the sum of the epsilons of I squared. It's epsilon 1 times epsilon 1 plus epsilon 2 times epsilon 2. So I get the sum of the squares. So we can say that this minimum is really equal to epsilon transpose times epsilon as a vector. Now that's useful because I'm going to come back and do that to this Z minus this H. Okay? So let's move the paper up. I think I'll let that rest right there for a minute. Let's go back now and look at this epsilon. So we'll say epsilon equals Z minus H, a matrix, times X. And I want epsilon transpose times epsilon. Okay, so that, and now I'm going to call that, that's a single number. That's a single number, it's a scalar, and that's J, and that's going to be minimized, okay? That's going to be the minimum. We're going to try to minimize that number, and it's the sum of the squares. Well, if you have this identity over here, so epsilon transpose is equal to Z transpose, what is this thing? Well, the transpose of a product is the product of the transposes in the reverse order. So that comes out X transpose H transpose. Incidentally, I wrote a little program. I'll show you the results of it later today. If there was one area where I didn't like what MATLAB did, I wish they'd have been able to put the letter T in it somehow, but they didn't. In MATLAB, transpose of a vector or a matrix is, for example, H transpose is H with a quote mark, a single quote mark next to it. So if I have the matrix H, then in MATLAB, that transpose, H transpose, comes out to be H like that. And I suppose that's a little bit like HT, but I've never thought that was. I wish they'd have been able to come up with a different notation that actually had the letter T, and they didn't. So I'll live with it anyway. My little difficulty. So now, if that's the case, then this is equal to epsilon. Let's say epsilon transpose times epsilon is equal to Z transpose minus X transpose H transpose times Z minus HX. So this is a matrix vector. We can put the brackets and underscore the vectors like that. And then when you multiply this out, so J, it comes out to be Z transpose Z minus X transpose H transpose Z. So that's these first two terms. Then we get minus Z transpose HX. And last of all, we get plus X transpose H transpose HX. But notice that we're multiplying the H matrix times its own transforms over here. It turns out that these two terms are equal to each other, and the usual way is to just write that as minus 2 Z transpose HX. Okay, these two are the same. This one here is simply the y values. It doesn't have any a or b. If it doesn't have any a or b, no x matrix in it, well, then this is just a constant. So this doesn't matter. I won't change its value in any way. So I can throw it out, and then I can say plus X transpose H transpose HX. That's J. That's a single number, and it's equal to this long thing here. And what do you do to minimize something? What do you do to minimize something? You take the derivative with respect to each independent variable and set the derivatives equal to 0. That's back to calculus 1, if you will. And once you got to be a graduate student, well, then we don't write all the derivative. We write it as a gradient. The gradient of J with respect to X. That's simply a vector, which is this is a vector that's got dj dx1, dj dx2, etc. And this is equal to the manipulations for this are in the book. I'm not gonna go into them now, but this is equal to minus 2 H transpose Z plus 2 H transpose HX, and we want that to go to 0. So we want to know, where does the gradient of J go to the 0 vector, 0, 0, 0? That's the minimum, and the answer is X. The estimate, the solution for this is at H transpose H inverse H transpose Z. Okay. This has got a name. It's called a pseudo-inverse. It says I'm going to invert a set of equations where I have more equations than unknowns. That straight line function, I can have 100 points. I could have 100 points, but only 2 unknowns, A and B. So I could have 100 equations. Now let's go back and let's actually do a numerical numerical problem, just to show you what this looks like. And I actually started to look for a piece of graph paper. Do you guys even know what a piece of graph paper is? Nobody uses graph paper anymore. If you want a graph, you have Excel, or you have a MATLAB draw it for you on just on the screen, and you print it. Back when I was your age, as they say, we used graph paper, and here would be a nice chance to have it. I don't have any, so let's just make some marks here. We'll try to make them roughly equal distant. So here's 1, 2, 3. And my first point up here is the point 1, 1.5. So this is y and this is x. And then my second point is down here, 2, 0.8. And the third point over here is going to be 3 and 2.2. 3, 2.2. So there's my 3 points. Now, let's go back again, and we'll say, okay, remember that the vector z has got y1, y2, y3. So the vector z is 1.5, 0.8, 1.2. And the H vector has, the H matrix has x1 and a 1, x2 and a 1, x3 and a 1. So that's simply, here I spaced them out on the even coordinates, so it's 1, 1, 2, 1, 3, 1. And I'm looking for the vector x, which has got a and b. I just need the two. I need x1 and x2. Those are the slope and the intercept of my straight line. And I wrote a MATLAB program. I can if I'm sharp enough today, which might be kind of questionable, but in any event, you define H as 1, 1, 2, 1, 3, 1. Okay? You can do this on your own on MATLAB to test it out. And then you have the vector Z, which is 1.5, 0.8, and 2.2. What did I? I'm sorry, 2.2. This is 2.2. And there's the other bracket. So they're in MATLAB, I have defined a matrix H, and I've defined the vector Z. And then X is equal to is equal to, and I did it this way, the inverse of H. Okay, there's the transpose, then you multiply that times H, then you multiply that times H transpose again, and multiply that times Z. Okay? You don't need an underline. This is MATLAB. And you get this vector X. And then I did the following, and I said A equals X1 and B equals X2. So that gives me the A and B. And it turns out for this example, A equals 0.35 and B equals 0.8. So if we go back to our thing like this, it's going to intercept around here. Well, let me come back down here. I'll tell you where the y1, which is equal to 0.35 times the value of x1 plus 0.8. y1 turns out to be 1.15, and y2, which is 0.35 times 2 plus 0.8, that comes out to be 1.5. y3, without writing the equation, is 185. So I can show you the points on my graph up here. At 1, it comes out 1.15. It's about here. At 2, it's 1.5, and at 3, it's 1.85. So it's not quite up to 2, but we get a straight line, and that's the straight line. And the error is the sum of the error squared of each error squared is the minimum that it could be. So that's the best line that we could in the least squares sense. So now what I'm going to do is I'm going to show you that especially with the linear power flow, we can do the same thing. And then we'll talk about the AC power flow, the fact that we can do that with AC. Here is I have this little power system with 3 buses in it. This bus has a load, and so 1, 2, 3. And in the problem we give you the values of x1 2 equals 0.2, x1 3 is 0.4, x2 3 is 0.25. So we have 3 measurements on this thing, and we put a measurement here. I'm going to draw it real big, and I'm going to call that M12. So M12 is the measurement of flow 1, 2. And I have a measurement here, which is going to I call this M13. So M13 measurement of flow 1 to 3, and similarly M23 is a measurement of flow. Actually, I'm sorry, 3 to 2, and there's a reason for doing it that way. Is a measurement 3 to 2, and that's down here. I like to have the flow. We always define the flow on a transmission line at the end of the bus as going away from the bus, and you always say the flow is the equation is this minus this. Okay, so we'll put those equations in. So the flow here is 3 to 2. It's the flow 3 to 2. Flow 3 2. Oh, that's easy. Well then, I'm gonna and wherever there's a measurement, there's a corresponding power system variable, which is a function of the state variables. Now, in the case of our linear power flow, that's just thetas. That's a vector of theta. In the AC, it's a function of a vector of voltage magnitudes and phase angles. So for each measurement, there's a corresponding, so we said here, for each, the measurement 1, 2, the corresponding is flow, 1 to 2, and that is equal to 1 over x12, theta 1 minus theta 2. So there's a corresponding variable which is a function of, meaning a mathematical function. Okay, so if I knew the state variables, then I could calculate that power system variable and compare it to the measurement. Okay, so I'm measuring a variable. I'm measuring in an AC system. I could be measuring power. I could be measuring real power, I could be measuring reactive power, I could be measuring just the voltage. In which case there's a very simple function, that is, the function is the voltage magnitude that I can measure. I measure the voltage magnitude, and that I'm actually measuring a state variable. Nowadays I can measure a phase angle as long as I designate one bus on the system as the reference bus with 0, then I can always measure the difference between that and the other bus, and therefore I can measure the phase angle. We'll go into that later. This is the function, okay, and that's the variable. Okay, this is the variable, and this is the function that gives us the value of that variable as a function of the state variables, and this is the measurement. Okay, now the measurement is something that we went out in this little power system. We went out and we measured it on the system. Measuring power flows on a system consists of, we have to actually measure the voltage, measure the current, and that's done with what are called PTs and CTs in the classic sense. PT standing for, let's just give you a little lesson here. PT is a potential transformer, and a CT is a current transformer. Now, to do phase angle measurements, they ended up with digital systems where they would sample, and they would literally sample the waveform, the sine waveform, and they would give you their interpretation of where it peaked. So they could tell you, when we say voltage on a sine wave, we mean the voltage of the sine wave at its peak. And that became a much more accurate measure of voltage and current. They do the same thing. And so classical cases, though, they did a measurement of the potential transformer off the current transformer. It's a transformer. It literally steps down the voltage to a low value, and it's used for protection. The relay equipment reads those PT and CT values, and we measure off of those as well. Classical ones didn't use anything with transistors. They used magnetic circuits that would give them a value fairly accurately proportional to the P or the Q or the voltage magnitude and so forth. Anyway, that's beside the point. Let's go back to this. There's a function of the state variables which corresponds to the variable, and that particular variable, we're going to measure it with something. Now, I often would tell my students that this has an actual value. I don't want to use the word real, but that's the actual value that's out there, And this is the measured value. Not to be confused with the actual value. The measured value has errors. The PT, CT are not as accurate as we thought. Whatever. The sample time was not the same as all the other measurements, therefore there's a time skew, introduces an error. The measured value has an error. But the actual value is what we're trying to get at. So that, it is what it is. It doesn't have an error, it just is. And we're trying to estimate, in the end, we want to estimate these guys. Okay, so I'm going to put a question mark. We're trying to estimate theta 1 and theta 2. Now, if you think about it, you look at that and you say, I have 3 buses on this system. If I just have a value for M12, I can't estimate theta 1 and theta 2. I can accurately tell you what the difference between theta 1 and theta 2 is, but that doesn't do me any good at all. So we'll just stop. We'll just drop that thread right there for now. So, but I want to make sure that you understand that there's a measured value, there's the actual value that we're concerned with, and that is a function of the state. We'll get it up there so they can see. Here's the actual value. It's a function of the estimate, the state variables, and they have a value 2, an actual value 2. Now, this being an error means that in the end, when I estimate the phase angles, they're going to have a small error as well. I don't need to go into that just yet. But let's keep going here. I may come back to that. All right, so let's write all my equations now. M12 equals flow, 12 equals 1 over x12, theta 1 minus theta 2. M13 equals flow, 13 equals 1 over x13, theta 1 minus theta 3, but theta 3 is a 0, so theta 3 we already know is the reference. Did I say that? Did I say that? Go back to this page. This is the reference, and so we're going to dictate that theta 3 equals 0. I'm sorry. So theta 3 is equal to 0. And last of all, M32 is flow. 32 equals 1 over x 23 or 32 doesn't matter. And this is theta 3 minus theta 2, and I'll draw that one. That's 0. That's 0 as well. So this equation here is really 1 over x13 times theta 1. And this is really just minus 1 over x23 times theta 2. Get it right. Theta 2, because theta 3 is 0. There's a minus sign in the middle there. That's why that minus comes up. So if that's the case, then Z is going to be the actual measured value. Okay, Z1, 2, Z1, 3, Z3, 2. Measured values equal the flow 1, 2, etc. Flow 1, 3, flow 3, 2 equals, and now I'm going to go to my H notation here. 1 over x12 minus 1 over x12. And over here I have theta 1 and theta 2. 1 over x13, 0, 0, minus 1 over x, 2, 3. Okay, so notice now that I have, in here, I have 3 equations. Okay, I have 3 equations, and these are the unknowns, and I have 2 unknowns. And typically you want that. In a state estimator, you want many more measurements than states. That will give you a much more accurate estimate of what the state of the system is. Well, this is we're gonna show that this is that this solution is done in the same way that we did the straight line regression, fitting a straight line to some points. But I want to talk about one other aspect, and that is that measurements have we can have poor measurements, and I can have very good measurements. What do I mean by poor and good? I used to use this example. It's interesting here. I used to use this example. I said poor measurements. You go down to the local Radio Shack and you pick up a little meter that costs $3. Okay, so here's a $3, and you get it from Radio Shack. Now the reason I was chuckling is because I'm not sure students even know who or what Radio Shack is anymore. I guess there are still some. Back in my day, when I was in school, and for many years, Radio Shack was an electronics store. They even had one of the very first personal computers called a TRS-80. That was made by Radio Shack. That's their brand name. The corporation name was Tandy Corporation. But I think they're all gone now. I think they're out of business, or at least you don't see Radio Shack. But they had very inexpensive stuff. You'd go in there and buy transistors, capacitors, resistors, transformers. You could buy components and build things if you were so inclined. And they had very inexpensive. I used to say you got a Radio Shack meter, and over here for $3,000, you get one from Hewlett Packard. Now, once again, you guys probably know Hewlett Packard for computers, laptops, and especially printers and scanners, especially printers. They're one of the biggest printer manufacturers in the world. But when they started out after the Second World War, there were 2 guys, Hewlett and Packard, in Palo Alto, California, and they made some of the absolute best, most accurate, stable measuring equipment, and signal generators and oscilloscopes. Their test equipment, I'm sure that they still make very, very good test equipment, but they're not the only one in it anymore, and they branched into computers many years ago. But Hewlett Packard was known, okay, as extremely accurate. Now, let me just show you here. Here's we're trying to measure a value out here. So this is x, and this is x actual. But when I take a measurement of it, I get a hit like this, and then I get another one over here, and sometimes I get them like this, and I keep measuring, and I get dots like that. Well, if I have a very, very good measurement and I do a histogram, I get something like this. Now, what we say is, we say that the measured value, Z, is equal to the X actual value plus an error, which will give this Greek letter zeta. So this is the error. And the error goes by a normal distribution. Normal distribution, n with a mean of 0 and a standard deviation. So this has a small sigma. If I, on the other hand, so this would be a good meter over here. This is our HP meter. And then I wanted to measure it, and I started measuring it with the Radio Shack. I'm getting values that are way out here, and I'm getting some of them way out here, and the distribution looks like this. Now, once again, Z equals X plus this eta, and the eta is normal, 0 mean, and sigma. Well, we say that the good measurement has a small sigma, and this has a large sigma. Okay? Small sigma, large sigma. And what we're going to do now is we're going to say, well, you know, if I'm going to combine measurements used that are lousy, poor equipment, and I'm going to combine that with measurements that are really good, I'm going to include this sigma as follows. I'm going to say I'm going to define J as the sum of the measured value, which the measurement, which is Z I, minus, here's my Fi of whatever the state variables are. Okay, that's you can put X in there, divided by sigma, and then squared. Now what we'll put an indicator down here, an index. I equals 1 to the number of measurements. What this does is, if sigma is small, then it gives greater weight. If this is small, see, if this is small, right, then it's as if I'm amplifying this thing up here. And therefore, when I do the least squares, I'll try and drive the measurement, the function, to the measured value. If sigma is large, we say that gives a reduced weight to, let's see, to Zi. So if the Z is large, well, that makes this into a small number to begin with. Even when you square it doesn't matter. Even if it's a big error up here, it's already got this big number down in here. So small sigma will amplify, large sigma will reduce it. And so this results in the term weighted least squares, or you'll see that term, weighted least squares, WLS. If you take a statistics course And by the way, I'll put in a plug. In the University of Minnesota, we actually have a statistics department. We have a department. I believe it's in. In fact, I should say I'm not sure if it's in the College of Science and Engineering, because it does a lot of work with biology and medical, and so they teach statistics. And I've encouraged students over the years, take courses in statistics no matter what you do. Sooner or later you're going to be doing something with statistics. This is also, this minimizing J is called the maximum likelihood estimate. It's the likelihood function is the probability. They say, well, what is the, give me the maximum probability of getting these measurements with given the errors that we have, and I will minimize that. That's called the maximum likelihood, the best. So if you take a statistics course, you'll learn about these. But take a statistics. You ought to have one good statistics course. When I was in graduate school, when I was in your age, I took a 2-semester course in probability theory, and then I took a 2-semester course in statistics. So this least squares thing was no great difficulty. When we got later on, I got to studying state estimation. Well, remember that I said J equals Z, that's the measurement, minus f of x, and then I said that that's going to be hx. What I'm going to do is and then I put this is transpose here. I'm going to stick something in the middle here called R inverse, and I'll show you what that is in a minute. The same thing, z mesh minus f of x. So these two were the same that we had before. This is transpose, and then I multiplied it out. I stuck this in here. Well, this is just a vector, a matrix R. It's got sigma 1 squared, sigma 2 squared, sigma, and this is the m is the number of measurements, like that. And so when you invert it, our inverse has got 1 over sigma 1 squared, 1 over sigma 2 squared, etc. So that's the weighting. They call that the weighting matrix. And it just builds this weighting into the problem. And the solution then for the estimate, this is again worked out in the text. I'm not going to do it here. It's in the lectures. It's in the textbook. H transpose R inverse H inverse H transpose R inverse. Let's just write a Z here with the little bar. Now there's Z. Okay. And that's the estimate that gives you the minimum value here, but it's minimum on the weighted sense. And what I'm going to show you now is that we go back to our little 3-bus problem again. So here, and let's, this is a generator, a load, and a generator. This is the reference bus. 1, 2, 3. I gave you the x values before, and I said that, and I set the problem up so that I'd have nice whole numbers. So this is the actual value, 60 and 5 megawatts. This is 65 then. This is 100, and this is 40. and this is 35. So the generation 35 and 65 gives you 100 megawatts of generation in. There's no losses, so we get 100 megawatts out. And these are the flows, nice whole numbers, 40, 60, and 5. Okay, so these are the actual values. Actual values. Okay, so then we came along and we did some measurements, and I will put them up here in red. So here's the measured values. Measured values. M12 actually comes out at 62. M13 comes out at 6. M32 comes out at 37. Where did I get those? I made them up. I just put some numbers down that are slightly different than the actual values. Remember when you solve, I want to go back to this again, and those of you that are, that are doing this course, the flow value is in per unit is equal to 1 over x, and the x is in per unit, and theta minus theta, these are in radians, and per unit, so this is megawatts here, and so this is 6.2 per unit. This is 0.06 per unit. This is equal to 3.7 per unit. Okay. When you solve, you've got to make sure you use per unit values because the x is in per unit and the theta is in radians. That's the way we solve these problems. So let's come back and say, okay, look, suppose let's call it let's use green just to show that we're going to have case 1. Use only M13 and M32. Now I can tell you, and you will recognize eventually, that if the number of measurements is exactly equal to the number of unknown states, then I will match these values precisely. I will end up with 2 equations and 2 unknowns. I will not need least squares, although the least squares equations will give me the correct answer. And when I do that, this is what I get. Here's my load, my generator, another generator over here, 1, 2, 3. In here, I get 58.25. Here, remember, here I'm using this one, so I'll put a little check mark next to it, and I'm using this one. So here I get 6, and here I get what, 37. So these are perfect, and so I match them perfectly. And this one comes out at 58.25, which is quite different than 60. So the fact that you matched 2 of them means that this guy is off. And you say, well, okay, and the problem here is that you could, if you went and got these measurements and you didn't want to do anything with least squares, you could set it up and solve for the power system just using 2 measurements and estimating 2 phase angles. But then you get this flow up here that's not correct. All right, you say, that's no good. So let's go and we'll do it with, let's call it case two. And I'm going to use M12 and M32. Now, the problem is that I will perfectly match this one and this one. We know that that's what's going to happen because that's what the math demands, that we have two equations and two unknowns, so we solve exactly that way. And it turns out that we end up with 62. That's the measurement up there, 62. And we end up with 37 down here, 37. But this guy over here gets 7.875. So this guy gets all the error pushed on it, and this one matches 37. This one matches 62. You can't read that. That's 37. 37 and 62. So we matched those two, and then this one goes off. So that's the wrong way to do it, to try to just say, well, I'll pick these and look at the solution. And then I'll pick these other. Can't do it that way. You simply can't do it that way. So now we come along and we say, look, I took Wallenberg's course at the University of Minnesota, so I'm going to take the case 3 using weighted least squares estimate. Okay, and that, and I think I put all the sigmas of that value, something like that. As long as they're equal, it doesn't matter. If the weightings are all equal, then it might just be 1. You'll still get the same answer. And there is an example in the book where we gave one of them a much larger value, and I'll show you with going back to that line example, the fitting of the line, what happens now. Weighted least squares. This one comes out 61.4. This one comes out 7.1. And this one comes out at 37.7. And remember that the actual value here is 40. The actual value here is 5. Pardon me. The actual value here is 60. So it gives you it gives you a little better picture, not completely better, but it gives you a better picture than we had with just using two measures. It doesn't force all the error. It spreads it around, and overall the sum of the squares are better off. Now, if we go back, suppose then that I said, well, let's take my sigma. I don't know. I don't have the book open. I'm not going to jump into it. But suppose I said one of the sigmas, sigma for one of the measurements is 0.01, and the next one is 0.01, and then I had a sigma equals 0.0001. So here's my two Radio Shack meters, and here's my HP meter. Really good one. Really, really good. Okay? Temperature controlled and compensated for every possible error that could be there, whereas these are just slapped together in the factory and whatever. What'll happen is that the outcome variable, the estimated variable here, will come very close to the measurement. And what it's like is if remember I had my three measurements here, and this guy was up here someplace. So there was my three values, of y and x. And I said, you know, I've got this line. Suppose I had said this one is going to have a sigma. So this one is going to have a very small sigma, and this will have these two values will have larger sigma. Now this one is the really good. What does that do? Well, in practical, it means that it's going to find the line that just goes right through it. That's what that means. It's going to drive the line that goes right through it. Now, if you made all of them this small, then nothing changes. Okay, the only time you get a shifting of the line or the shifting of the state estimate is if there are differences in these sigmas, and that's the difference between a good meter and a bad meter. What we're going to show next time, because this now, and those of you that took the tour of OSI last week, they talked about the fact you use the state estimator to give you the best values for the power system variables that you can. There are many other reasons for running the state estimator. It can give you a value for, let's say, a flow which is not measured. That's extremely useful. Which is not measured. Here's one that makes it really is the one that some people say is more valuable than just estimating the variables. It can tell us if one measurement or more, we got to put this on here to be honest, tell us if one measurement or more is bad. I was saying last Friday, sometimes you get measurements that they've been out there in the substation, and they were wired up 30 years ago, and they never went out and checked everything, and it turned out they wired them up backwards. It happens. So you end up with a substation here. And maybe you've just got power flows coming in and going out, and it turns out that they're supposed to be measuring flows like this, and by Jove, they're telling you that the flows are like that, and they all add up still, but they're all negatives. They're all backwards, and you think, oh, that can't be. It is. It happens. That's a bad measurement, or it sometimes simply means that the transducer itself, or whatever is in there, the electronics, the magnetic circuits, whatever, goes bad. And the state estimator can tell you if there is a bad one, and hopefully it can actually identify the bad measurement. Well, there's two things that you want to do then. Number one, stop using it. Take its value out of the set of measurements that you're putting into the state estimator. And the other thing you do is you send technicians to the substation to fix it. And a lot of people have told me over the years that having a state estimator detecting, this is called the detecting problem. Detecting and identifying of bad measurements makes the estimator, just that alone, makes the estimator really worthwhile. That they're very happy to have that state estimator to tell them where things are bad in the power system. Otherwise, they're making decisions on measurements that are bad. Suppose they're looking at it and saying, is that power flow on that line getting close to its limit? And they look at it and they say, let's see, the limit is 250 megawatts. Oh, it's only at 210. We're fine. Well, in fact, the measurement is bad, and it's not actually flowing at 250. It's 280, and it's overloading. So you're making a bad decision. Something can happen because you're getting a false picture from a bad measurement. Measurements go bad. And so the first time I put a state estimator in, the people that were there eventually, they told us whenever it identifies a bad measurement, we send a technician out to either replace it or to see if they can fix it. Usually they probably replace it and then bring equipment back and fix it back at the home office, so to speak. Okay, so that is power system state estimation. Next time we're going to go through, there's a lot of other topics that we get into power system state estimation. We'll get into a little bit into the detection and identify how they do that. There's another thing called observability. When do you have enough measurements to actually do the state estimate? And it can turn out that you may not have enough measurements to do it. That's more of a building, a planning problem. Other issues like that, and how do you solve an AC where you've got this nonlinear network? Just a little sidebar here at the very end. The fellow that started the work on state estimation, I was there when he presented the first papers. Was a professor from MIT, Fred Schweppe. He was a control systems theorist, and you know what he did the following. He's got a rocket over here, and the rocket is going to go up, and they're going to have radar systems here on the ground. They're going to have several radars, and the radar will track an azimuth angle like this and a distance. So here's D1 and theta 1 and D2 and theta 2, etc. They'll have many of these things, and they're tracking the same rocket, and they want to know where is the position. And there's lots of error in the azimuth or the angle and the distance. And also, of course, there would be a horizontal angle. And so they used state estimation to tell where's this rocket going up. The state of the rocket, of course, is the it's got a set of three-dimensional coordinates. So it's got an X, Y, Z, if you will, set of coordinates. And it also has velocity 1, velocity 2, and 3, and maybe acceleration and so on. It's got a lot of state variables. And they've got the only way they tell where it is by radar signals, which are not that accurate. So they used, and from there, he had gone to American Electric Power and seen the difficulty they had matching the power flow. He applied the same theory. Extremely bright guy. Extremely good. Okay, we will, on that note, we'll credit where credit is due to Fred Schweppe. We will bid you adieu, and I'm going to leave the meeting. See you on Thursday.